I want you to just take a second and picture the hallway of your home.
Right.
Focus on that little plastic box plugged into the wall, maybe near the baseboard or, mounted up near the ceiling.
Yeah, everybody has one.
Exactly. That $25 carbon monoxide detector you picked up at the hardware store, it just sits there with this little green LED light glowing, offering this, immense peace of mind.
It really does feel like this ultimate safety net while you sleep.
It does. But the mission of today's deep dive into our sources is to completely shatter that illusion.
Well, yeah, we have a massive stack of material in front of us today. We're talking technical manuals, HVAC industry research, diagnostic guides.
And all of it, all of it points to one terrifying reality. That little plastic box is actually legally engineered to ignore a slow, chronic leak that could be poisoning you right now.
It's a really profound disconnect between what we assume we're buying and what the technology is, actually designed to do. So today is really about understanding why our residential safety nets have these massive blind spots. We're going to look at the biology of what happens when they fail and how you can empower yourself with the right knowledge before the cold winter hits.
Because honestly, thinking that a basic $25 detector keeps you completely safe from carbon monoxide is, it's like owning an umbrella that only opens in a Category 5 hurricane.
That's a great way to put it.
Right, but it completely ignores a freezing winter drizzle.
Yeah.
You're still going to get soaked, or in this case, seriously sick.
Exactly. But to understand how we fix this, we first have to figure out what that machine on the wall is actually doing.
So where do we start?
We have to look at the manufacturing regulations. There's a very specific federal standard for residential CO detectors.
Wow.
In the industry, it's known as the Underwriters Laboratory Standard 2034, or just UL 2034.
And reading through the actual text of UL 2034 is, frankly, eye-opening, because it mandates this very specific, inflexible set of numbers.
Right, it's entirely numbers-based.
A standard detector will only sound the alarm if carbon monoxide levels hit 70 parts per million for 3 to 4 hours. Or if it hits 150 parts per million, it takes anywhere from 10 to 50 minutes to go off.
Yeah, and then there's the extreme scenario.
Right. In the event of a massive sudden surge, it has to hit 400 parts per million for 4 to 15 minutes before making a sound. That is the baseline spec.
Meaning, if the concentration of poisonous gas in your home is sitting at, say, 30 parts per million.
Or 45.
Right, or even 65, that detector can just sit there in absolute silence indefinitely.
Okay, I got to push back on that logic.
Go for it.
Why on earth would federal regulators intentionally build a life-saving device to completely ignore a 30 part per million leak? That sounds incredibly dangerous.
Well, you really have to look at the context of what those engineers were trying to achieve at the time. These detectors are built specifically and really exclusively for the catastrophic acute scenario.
Like the headline grab and stuff.
Exactly. They're looking for the sudden, massive leak that requires you to wake up, grab your family, and evacuate the building immediately. The kind of event that makes the evening news.
Right.
They're not designed to be, sensitive air quality monitors.
Because if they were too sensitive, they just go off constantly.
Precisely. If they alarmed at 15 or 30 parts per million, you might get all this nuisance tripping from minor temporary sources.
Like what?
Well, imagine you start a car in an attached garage, and the wind blows a tiny puff of exhaust under the door when you open it.
Oh, sure.
Or you burn a piece of toast. Or maybe you use a gas stove without the vent fan on. To prevent false alarms, the baseline was set intentionally high. Regulators wanted to avoid a boy who cried wolf scenario.
That makes sense.
When that alarm shrieks at 2 in the morning, they need you to know it's a life or death emergency, not just a draft from the garage.
So it's essentially a binary system. It's either everything is fine or run for your life.
Yeah, exactly.
But they completely left out a setting for you have a slow, insidious problem developing.
They are completely blind to chronic exposure.
Wow. So if the machine on the wall is ignoring a 30 part per million leak, what is that invisible, unrecorded gas actually doing to the human body over a long winter?
It's doing a lot of damage.
Because you might not be triggering an alarm, but you are absolutely breathing it in every single day.
This is where the biology becomes incredibly insidious. Yeah. To understand the damage, you have to understand how oxygen moves through your body.
Okay, break it down for me.
You have hemoglobin in your red blood cells. Think of it like a microscopic delivery truck. In a normal, healthy environment, oxygen hops onto the truck in your lungs, rides through your bloodstream, and hops off to feed your cells.
Carbon monoxide disrupts that delivery system.
It doesn't just disrupt it, it completely hijacks it. Carbon monoxide binds to that hemoglobin molecule with an affinity that is, get this, roughly 200 times stronger than oxygen.
200 times.
Yeah. It's like molecular musical chairs, and the carbon monoxide is this bully that just refuses to get out of the seat.
So the oxygen literally can't get a ride.
Exactly. So even at low levels, like 30 parts per million, if you're breathing that in for 8 hours a night for 3 months straight during winter, your blood loses its ability to carry oxygen.
That sounds awful.
Your body is constantly being starved on a cellular level.
And the physical symptoms of that cellular starvation are terrifying, mostly because they're so subtle.
Very subtle.
We're talking about chronic, low-grade headaches, mild nausea that just won't go away, a persistent brain fog, and this deep, heavy fatigue that no amount of morning coffee or extra sleep can fix.
What's fascinating here is how perfectly those specific symptoms masquerade as common winter illnesses.
Oh, I didn't even think about that.
Think about it. When does your furnace run the most? February.
Right.
When is peak flu season? February. When people feel tired, achy, and foggy in the dead of winter, they don't jump to the conclusion that they're being slowly poisoned.
No, of course not. You just think you caught a bug going around the office.
Exactly, or that you're just dealing with seasonal depression. The symptoms completely bypass our critical thinking.
That brings up a really practical diagnostic tool we came across in the sources, the Grandma's House test.
Oh, I love this one.
It's such a brilliant way to bypass that confusion. If your whole family has flu-like symptoms in the middle of February, but miraculously, everyone starts feeling better when you pack up and leave the house for the weekend to go visit Grandma.
And then you all feel sick again the exact moment you walk back through your own front door.
Yes. If that happens, you have a carbon monoxide problem until proven otherwise.
It isolates the environmental variable. If the sickness is tied strictly to the physical location, it's not a virus.
And it's not just the humans in the house we need to watch either. We also have modern-day canaries in the coal mine.
Right, our pets.
Because back in the day, miners actually used birds, since their tiny respiratory systems would process poisonous gas way faster than a human, giving the miners a visual warning.
A tragic but effective warning system.
Today, it's our pets. Birds are still highly sensitive, obviously, but even dogs and cats will react. If your cat is suddenly sleeping 18 hours a day in a corner, or your usually energetic dog becomes incredibly lethargic and refuses to play.
Those are massive red flags.
Huge. They have smaller lung capacities and higher respiration rates than we do, so that 30 parts per million hits them much harder and much faster.
And through all of this, the dog acting lethargic, your lingering headache, the brain fog, your hallway detector is completely silent.
Just sitting there.
That green light is just staring back at you, falsely signaling that the air is clean.
So if our bodies are feeling it, and our pets are feeling it, but the hallway detector is intentionally blind to it, how on earth do we actually find a 30 part per million leak?
For a very long time, finding these microleaks was incredibly difficult in a residential setting. Technicians relied mostly on visual cues.
Right.
But the technological game changer that solves this is the handheld digital combustion analyzer.
Which is funny because I always assumed HVAC techs just looked at the flame in the furnace to see if it was burning blue instead of yellow.
A lot of them still do, unfortunately.
But these combustion analyzers, they sound like something out of a science lab.
They essentially are. For decades, combustion analyzers were the gold standard in commercial settings. Think massive boiler rooms in skyscrapers or industrial heating plants.
So why weren't they in homes?
The problem was the economics. A good handheld unit used to cost between $1,500 and $3,000, and the sensors had to be constantly recalibrated.
Oh, wow. Yeah, that's pricey.
It was a massive capital investment for a small residential HVAC company, so they just didn't buy them.
But the tech has evolved. According to the deep dive sources, the price has plummeted. You can get a highly sensitive, durable residential analyzer now for, what, $400 to $900?
Yeah, they've become incredibly accessible.
And the sensitivity's wild. They use these electrochemical sensors that literally sniff the individual molecules of gas, reacting to them to create a tiny electrical current.
It's brilliant engineering.
They can detect carbon monoxide down to 5 parts per million. And the really premium units can read down to 1 single part per million.
It takes all the guesswork and visual estimating completely out of the equation. The technician isn't just looking at the color of a flame anymore. They're getting precise, real-time chemical data about exactly how that furnace is operating.
I love data.
When they use this tool, they're checking what the industry calls the Big Four metrics.
Okay, let's walk through the big four because this seems like the exact data every homeowner should be demanding. What's the first metric?
The first is carbon monoxide in the flue gas. The flue is the chimney. It's the exhaust pipe carrying the burned gases out of your house.
Got it.
Even a perfectly functioning furnace produces a little bit of carbon monoxide during the combustion process. On a healthy unit, the analyzer should read this number in the low single digits.
Okay, so a tiny bit in the exhaust pipe going outside is normal. What's the second metric?
The second is carbon monoxide in the supply air. The supply air is the warm air actually blowing out of your vents and into your living room.
And that number must be absolutely zero, period.
Exactly zero. Any reading above zero on the supply side means toxic exhaust is actively mixing with your breathing air.
That's a scary thought. What about the third metric?
The third is stack temperature. This is a brilliant measure of efficiency. When your furnace burns gas, the goal is to transfer that heat into the air circulating through your house.
Right, that's the whole point of a furnace.
The stack temperature tells the technician how hot the exhaust gas is as it leaves the house. If the stack temperature is too high, it means your furnace is failing to transfer the heat to your home.
Oh, so it's just venting the heat outside.
Yeah, you're essentially just paying to heat the sky outside your house.
Which hurts your wallet, but I guess it doesn't necessarily poison you.
True.
But the fourth metric is the one that really caught my attention in the research. Draft pressure.
Draft pressure is absolutely critical for safety, and it's something almost no homeowner ever thinks about until it fails.
I really need you to explain the physics here, because when I think of exhaust going up a chimney, I just think hot air rises. How does draft pressure become a safety hazard?
Think about the macro trend of modern housing construction. We've spent the last 30 years making our homes incredibly energy efficient. We seal up every crack with caulk. We install these heavy double-pane windows. We wrap the entire exterior of the house in weather-resistant barriers and thick insulation.
Basically making it airtight.
The modern house is essentially a sealed plastic bag.
Which is great for keeping the warm air in.
It is, until you introduce powerful exhaust fans. Imagine a freezing winter morning. All your windows are shut tight. You turn on a powerful modern kitchen exhaust hood to cook breakfast, or maybe you run 2 bathroom exhaust fans at the same time after showering.
Okay, I'm picturing it.
Because the house is so tightly sealed, those fans are forcefully pulling air out of the house, creating a zone of negative pressure inside.
So it's acting like a vacuum trying to suck air back in from anywhere it can?
Yes, and nature abhors a vacuum. The house is desperately trying to pull replacement air back inside. If the windows are sealed, the path of least resistance might be straight down your furnace chimney.
Wait, really?
Yeah. So instead of those dangerous hot flue gases floating safely up and out, that negative pressure literally pulls the exhaust backward down the chimney and spills it right into your basement or utility room. This is called backdrafting.
That is terrifying.
And a combustion analyzer with a draft probe catches this invisible aerodynamic failure on the very first test. It measures the micropascals of pressure in the chimney.
Wow.
Without that probe, the technician is literally just guessing if the exhaust is going out or coming back in.
So the analyzer catches the draft issues, but its most critical job, the reason it's an absolute non-negotiable necessity, is diagnosing the nightmare scenario hidden deep inside the furnace middle itself.
You're talking about the cracked heat exchanger. This is the structural failure that causes the slow, chronic poisoning we discussed earlier.
Let's visualize how this works, because the heat exchanger is the absolute core of your furnace.
It is.
Picture it like a completely sealed metal balloon sitting inside your home's air ducts. When your furnace turns on, the actual fire, the gas burner, is strictly inside that metal balloon.
Right.
It heats the metal up until it's blazing hot. Then your blower fan kicks on and pushes the air from your hallways across the outside of that hot metal balloon. The air absorbs the heat, gets warm, and blows back into your living room. Meanwhile, the toxic exhaust from the fire inside the balloon gets vented out the chimney. Your breathing air in the exhaust should never, ever touch.
But metal is ultimately subject to the laws of physics?
Right. If that metal balloon gets even a tiny microscopic hairline crack, the poison leaks out of the balloon and directly into the breathing air circulating through your home.
And we really have to consider why these cracks happen in the first place. It's a slow, relentless process of metal fatigue.
Like bending a paperclip.
Exactly like that. Think about taking a paperclip and bending it back and forth. Initially, it's fine, but eventually the metal stresses, weakens, and snaps.
Yeah, I've done that.
A heat exchanger goes through thousands of dramatic temperature changes every single winter. It goes from a cold room temperature to hundreds of degrees, expanding as it heats and contracting as it cools. Hot, cold, expand, contract, over and over again for years.
And the sources say a typical lifespan for a heat exchanger is only, what, 12 to 25 years?
Yeah, that's the standard range.
After about 12 years, that metal fatigue really starts setting in, and the risk of a crack climbs significantly. And there are really only a few ways a technician can actually find these cracks.
Right, there are three main ways.
First, a visual inspection using a borescope camera, snaking a tiny flexible camera into the dark hidden corners of the unit to look for rust or fissures.
Which is great if they can see it.
Second, the combustion analysis, where they watch the carbon monoxide levels spike on their digital screen the exact moment the blower fan kicks on and pushes air through the crack.
And they also use a pressure decay test.
Which is basically like testing a bicycle tire for a leak. They seal off the metal balloon, pressurize it, and see if it holds the air.
Exactly. And this structural degradation connects to a massive issue regarding our aging housing infrastructure. There's a specific example in the research highlighting the housing boom in Oklahoma between 1985 and 2005.
Oh, yeah, that was an interesting case study.
But really, millions of homes across the entire country were built during similar massive suburban booms. Those furnaces, installed during that 20-year window, are all currently hitting their 20 to 40-year mark.
So they're basically ticking time bombs.
We are looking at a perfect storm. You have an entire generation of heating infrastructure suffering from severe metal fatigue, and they are being pushed to their absolute limits on freezing January mornings. The conditions are perfectly primed for marginal heat exchangers to finally crack.
Knowing this technology exists and knowing our infrastructure is aging is great. But actually ensuring the technician you hire uses the right tools requires understanding the hidden economics of the HVAC industry.
This is so important.
We really need to demystify the infamous $49 tune-up.
Yes. This is where consumer awareness becomes your absolute best defense. Because the word tune-up is thrown around really loosely, and not all of them are created equal.
We've all seen them. The coupons in the local newspaper, the flyers in the mail, or the digital ads. Fall furnace tune-up, only $49.
Right.
If you start and think about the economics of running a business, the math on that just doesn't work. $49 barely pays for the gas in the technician's truck and the wear and tear on their tires, let alone an hourly wage, insurance, and the overhead of a company.
Which raises a very important question. What are you actually buying for $49?
Exactly.
The reality of the industry is that you are not buying a comprehensive safety diagnostic. The $49 tune-up is a very specific business model. It's a loss leader.
It's a foot in the door.
Exactly. It's a lead generator designed to get a salesperson in a technician's uniform into your basement. They spend 20 minutes with a clipboard, do a quick visual check, swap a cheap air filter, and look for a broken part they can sell you a highly marked up repair on.
It's a sales call disguised as maintenance.
Precisely. Nobody is breaking out a sensitive $900 digital combustion analyzer for a $49 visit.
Contrast that with a real comprehensive tune-up. The research highlights master technicians professionals who hold NATE certification, which is the industry's highest, most rigorous standard.
The NATE certified folks are the real deal.
A real tune-up from a professional like that costs closer to $229. It takes 90 minutes, not 20. And the combustion analyzer is treated as absolutely mandatory equipment. It comes off the truck on every single call, regardless of how old the furnace is.
Because knowledge is most valuable when it's applied correctly. When you pay that higher rate, you aren't just paying for parts, you are paying for the technician's time.
That makes total sense.
You're buying the 90 minutes required to turn the furnace on, let it run until it reaches a steady operating temperature, physically probe the flue, check the supply air, scope the heat exchanger with a camera, and verify the draft pressure in the chimney.
You're buying actual, measurable, scientifically verified safety.
Yes, exactly.
So how do we as homeowners guarantee we're getting the real deal and not just a sales pitch? I love this part of our sources because it puts the power back in your hands.
It really does.
When you call to book your winter furnace maintenance, you need to use 3 very specific magic phrases on the phone. Do not wait until the technician is standing in your basement. You ask these of the dispatcher when you are booking the appointment.
Preparation is key.
Here we go. Number 1, I want a combustion analysis included with the printout. That printout part is key. It proves they actually ran the numbers through the machine and aren't just making it up.
Hold them accountable.
Number 2, I want the heat exchanger inspected with a borescope if the unit is over 10 years old. Number 3, I want the carbon monoxide parts per million in the supply air verified at absolute zero.
That is a fantastic checklist.
If the person on the phone hesitates, hems and haws, or says something like, "We don't really do that, but we do a great visual check," hang up the phone. They do not have the equipment, and they are not doing a real safety check.
It is incredibly empowering to have that script. It completely shifts the dynamic of the transaction. You're no longer just hoping they do a good job. You are setting the technical standard for the work you're willing to pay for.
So where does this leave us with a little plastic box in the hallway?
Right, the $25 question.
Do not throw it away. In fact, keep your $25 hallway detector and go buy 2 more.
Absolutely.
Put one right outside the bedrooms and put one down by the furnace. They are your vital, absolute last line of defense. If something catastrophic happens at 2 in the morning, a sudden 400 part per million surge, that screeching alarm will wake you up, get you out of the house, and save your life.
They are entirely necessary.
But you must recognize that they are the floor of your safety system, not the ceiling. The digital combustion analyzer, in the hands of a trained professional who knows how to read the Big Four, is your first line of defense. It is the tool that catches the hairline crack, the slow leak, the negative draft pressure, 6 months before that plastic box ever makes a sound.
It's a fundamental shift from reactive safety to proactive safety.
Absolutely.
And, if we connect this to the bigger picture of how we build and live today, it leaves us with a rather provocative thought to mull over. We have built our entire residential safety codes around acute headline-grabbing disasters. We mandate alarms for the extremes, the massive fires, the sudden leaks.
Right.
But as our modern homes become tighter and tighter, sealed up like plastic bags for the sake of extreme energy efficiency, what other subtle, chronic environmental hazards are we trapping inside with us?
Oh, wow.
What other chemical or biological issues are quietly accumulating in our living spaces, slipping right past our legally mandated safety nets, simply because they aren't loud enough or fast enough to trigger a traditional alarm?
That definitely changes how you look at the air you're breathing inside your own home. The next time you walk down your hallway and see that little green light on the CO detector, remember? It's just an umbrella. And it's up to you to make sure you aren't standing in a freezing drizzle, blindly assuming you're dry. Ensure your first line of defense is actually doing its job.